This is lesson 2, gravity problems in one dimension. Okay, so we're starting off with gravity problems. All we're doing here is trying to get a feel for our equations of motion, just really getting to grips with the basics of using those. If you've done these before, fantastic, treat this as a bit of revision. Okay, so what we're looking at here in our first example, okay, if you read through your notes, once you get to example 1, a stone is thrown through vertically upwards at a speed of 14 meters per second, and we're asked to calculate as part A, what is the maximum height reached. Okay, now the key thing to note is that at the maximum height, velocity is 0. If you imagine how that stone's going to move, it's going to come up, and as it hits its maximum point to turn and come back down, at this exact point here, it for that split second stops dead in midair before it then comes back down. Okay, so at that exact moment, the velocity is 0. So anytime we're asked to find the maximum height in a gravity problem, v equals 0 is likely to be our key piece of information that allows us to calculate that. Okay. From there, we're just going to set up our equations of motion, or UVATs, SUVAT, whatever your preference is. Our initial velocity is 14, final velocity is 0. Acceleration, assuming we're on Earth, unless told otherwise, is always going to be negative 9.8. Time, we don't know, however, in this particular example, time is irrelevant, we're not asked anything to do with that. And displacement is that maximum height. Okay. All I've got to do now is select an appropriate equation of motion, plug the values in, and calculate. So I'm going to use v squared equals u squared plus 2as. V squared can be 0. U is 14, 14 squared is 196. 2 multiplied by the acceleration is 19.6. And we'll keep s as it is. Okay, so we've got 196, subtract 19.6s. Okay, I appreciate not showing up perfectly in the video, but I'm sure you'll get the grip. Okay. What we're then going to do is simply do a bit of rearranging. 19.6s equals 196, and so we divide through and we discover that s is 10 meters. Okay, nice and simple, nothing too complicated there. Okay. Part B is where we have to do a little bit more thinking. Okay, so we're asked for how long is the stone in the air. So we're trying to find the total time between the stone being thrown upwards and it coming back down to ground level. Okay. What we now have to consider then is that, again, our initial velocity is 14. However, when it comes back down, because we're assuming that there is no effective air resistance in this problem, the speed is going to be the same as it comes back down. Okay, so it's going to be negative 14 meters per second, but moving downwards, so negative 14. Acceleration is still going to be our negative 9.8, 1g. Time is now our key bit of information to find, and the overall displacement is 0 because we're measuring the time from the stone leaving a point and then returning to the exact same point. Okay, so in effect, it's actually not moved. We want to know what is the time value at which point the stone returns to its original position. Okay, what we're going to do there is, again, choose our equation of motion. I'm going to go with s equals ut plus half at squared. So we're going to say that 0 is 14t minus half of 9.8 is 4.9. Okay. And what you'll notice here is we've got a quadratic function equal to 0. And if you think back to your National 5 maths, what that means is we can take t as a common factor, 14 minus 4.9t. We can split this off into two problems. So we're told that the displacement is 0 when time equals 0. Well, we knew that. That's the point at which the stone is thrown upwards. So this isn't really the one we're interested in. Okay. 14 minus 4.9t equals 0. Okay. Rearrange that, we end up with t is 14 over 4.9, which gives us 2.8571. Let's call that 2.86 seconds. That is example 1 completed. My apologies, I've chopped off the bottom there. Okay, example 1. For example 2, we start to deal with, well, actually, hang on a minute, in real life, who throws a stone from ground level? Okay, so if you have a look at your example 2, stones are more commonly thrown from above ground level. Okay, so what we're going to do is actually say, well, if a stone is thrown under the same conditions, but this time it's thrown from a starting height of 1.4 meters, okay, let's calculate the same value, the same data in terms of the time in the air. Okay, so what we're going to do this time, for example 2, we're still going to set up our UVAS equation. We've still got an initial speed of 14 upwards. We don't know what the final speed is, okay, because we're starting from a height of 1.4, so the stone is now going to drop back down to ground level. Okay, so we don't actually know the final speed. We know the acceleration, because we're dealing again in Earth, is negative 9.8. Time is our big question mark, and the displacement, if you think about this, stone is starting from a height of 1.4 meters and being thrown up, is then coming back down to ground level. It has dropped by 1.4 meters overall. So our displacement is negative 1.4. Again, what we're going to do is start off with S equals ut plus half at squared. Okay. Negative 1.4 is 14t minus 4.9t squared. So you can see here all that's changed is that the displacement is now negative 1.4 rather than 0. Let me just neaten this up a wee bit for you. Okay, only thing that's changed so far. What we're now going to do is rearrange this, because, again, think back to National 5, if we have a quadratic, in order to solve it, it has to be equal to 0. Okay, I'm also going to do a bit of rearranging here, just so that we have our descending orders of t. So we've got negative 4.9t squared plus 14t. This moves over here and becomes positive, plus 1.4 equals 0. Okay. Again, think back to your National 5. What we have here are a, b, and c values that we can use in our quadratic equation. So t is equal to negative 14 plus or minus square root of 14 squared minus 4 times negative 4.9 times 1.4. I'm running out of space, but we'll manage. All over 2a. So, okay, I'm not going to run through the whole thing on the board here, because you should know how to use that. What we end up with are our t values as negative 0.0967 and 2.953. Now, obviously, because we're dealing with time, we don't really want that negative. If you think about it, if we were just tracking this, the time at which the height of the stone would be 0 would be before you threw it. So if we're purely assuming this acceleration due to Earth's gravity, the mathematical model gives us this. Okay, however, we know that t has to be greater than or equal to 0, so we're going to ignore that negative value there. Okay, what we're then going to do is just round this, and let's call that 2.95 seconds. Okay, and there's example 2. Okay, gravity problems in 1D. Have a look at the notes for further guidance.